Hello friends, today we are going to discuss choice of specific magnetic loading, that is BAV. We already discussed what is BAV in our earlier video. BAV is nothing but total flux in the air gap divided by area of flux in the air gap, that is BAV is equal to pi p divided by pi dl. Then while selecting BAV, following factors should be considered. First one is size of machine. We know output equation of three-phase induction motor, that is Q is equal to C0 into D square L Ns. Then D square L is inversely proportional to C0, that is output coefficient, but C0 is 11 BAV AC kW into 10 to the power minus 3, that is BAV is specific magnetic loading, AC is specific electric loading, kW winding factor into 10 to the power minus 3. Since here we are only talking about specific magnetic loading, that is C0 is directly proportional to BAV. C0 is directly proportional to BAV, and output coefficient C0 is inversely proportional to D square L. That is, as we increases the value of BAV, that is specific magnetic loading, the C0, that is output coefficient, is also increases since it is directly proportional. Since CO, that is output coefficient, increases, therefore D square L, that is size of machine or volume of active parts, is decreases since output coefficient is inversely proportional to D square L. Therefore, from this point we can say that as the value of BAV increases, size of machine decreases. Now, the second factor is iron loss, which is also known as core loss. Since iron loss is divided in two parts, that is hysteresis loss and eddy current loss. We know the relation of hysteresis loss, that is eta to the power 1.6 FV, and for eddy current loss eta is equal to B square F square T square. Maximum flux density Bm is, F is a frequency, phi is a volume. Bm is a maximum flux density, F is a frequency, T is a thickness of lamination. From these two equations, we can say that both hysteresis and eddy current loss are directly proportional to B average or Bm, that is maximum flux density. Therefore, as we increases the value of BAV, both hysteresis and eddy current loss, that is iron loss, increases. As losses increases, efficiency of the system decreases. Since efficiency is output power divided by input power, we can write input as output plus losses. Therefore, as losses increases, efficiency of the system decreases. Next, third point is frequency. Since again here hysteresis loss is directly proportional to frequency, as we discussed in above point, hysteresis loss is directly proportional to frequency, and eddy current loss is directly proportional to square of frequency. Therefore, core loss is also directly proportional to frequency. Since as value of frequency increases, core loss, that is core loss, also increases. Therefore, so BAV is select such that the iron losses are within the limits. Next, fourth point is power factor. As we know, BAV is equal to average flux density or specific magnetic loading is equal to phi p divided by phi dl. Here, as we increases the value of BAV, since phi has to be increased. Therefore, high value of flux is required. Therefore, to get high value of flux I mu, that is magnetizing component of current I mu, we should draw large magnetizing current since I mu is required to set up the flux in the air gap. Therefore, as the value of magnetizing current increases, cos phi, that is power factor, is inversely proportional to magnetizing current, that is I mu. Since I mu increases, power factor of the machine decreases. Therefore, as we select high value of BAV, that is specific magnetic loading, power factor of the system or machine decreases. The next point is overload capacity. Here, as we increases the value of, again value of BAV increases, phi, that is flux in the air gap, increases. Since as per the Faraday's law of electromagnetic induction, the magnitude of induced EMF is directly proportional to rate of change of flux linkages, that is N d phi by dt. Here, as we increase the value of flux, to maintain EMF constant, N has to be decreased. Therefore, since we know L is equal to N into phi divided by current. L is the inductance is equal to N number of turns, phi is the flux current. Here, as the value of N decreases, L also decreases since L is directly proportional to N. Therefore, as L decreases, XL is equal to 2 pi FL. We know the relation of inductive reactance, that is, as L decreases, XL also decreases, inductive reactance also decreases. We know diameter of circle diagram is inversely proportional to XS or XL, that is leakage reactance. Since here X is decreases, therefore diameter of circle diagram increases since both are inversely proportional to each other. Therefore, overload capacity of machine increases. Here, from above discussion, we can conclude that as we select the high value of BAV, that is average value of flux density, high value of BAV, therefore power factor of the machine decreases, losses increases, size of machine decreases, overload capacity of machine increases. These are the summary or conclusion from above discussion. Thank you.